Brahe, Kepler, and then Galileo have made great strides in taking these celestial objects and studying them as physical concepts that we can measure and discuss and hopefully understand. But the real understanding waited a few more decades for, as I promised, Isaac Newton. We're going to spend the next few clips following in the steps, the rather large steps, of Sir Isaac and seeing what it was that he taught us. And we're going to start at the beginning with mechanics, the science of motion, which is going to underlie everything else. So we're going to do some physics, bear with me. It's going to be intense. To study motion, the first thing we need to do is make mathematically precise what it is that Galileo said when he said an object retains its state of motion. So mathematically, the state of motion is represented by an object's velocity. Velocity is a physics concept. It means the speed with which something is moving along with its direction. So we denote it by this V with an arrow on top of it. V stands for velocity, and the arrow reminds us that this is a number, the speed at which something is moving, along with the direction, so that this ball can be moving at 1 meter per second to your left or my left, and at 1 meter per second to my right, or up or down, or in or out. And those, even if the speeds are the same, are different values of the velocity. Velocity can be thought of, as we know, speed is measured in meters per second because it is the change in position, in where you are, the distance divided by time. And velocity can change. The ball can start slowly and speed up. And its change is called the acceleration. So acceleration is the rate at which velocity changes, and acceleration is measured, therefore, in meters per second, the difference in velocity between the beginning and the end of an interval, divided by the length of the interval. The same way that velocity is distance divided by time, acceleration is velocity per time. And so the rate of change of velocity is an acceleration, and it's measured in meters per second squared. And like velocity, acceleration has a direction. So that if an object is moving to the left and speeding up, then its acceleration points to the left. If an object is moving to the left and slowing down, that means its velocity points to the left, but its acceleration points to the right, because the velocity is less to the left later in the interval than it was before. So acceleration, like velocity, has a direction. And in addition to expressing the fact that an object could be speeding up or slowing down, there can be a change of velocity that is associated with maintaining the same speed, but merely changing direction. If an object is moving to the left and starts moving towards the camera, this is a change in velocity even if the speed never changed. And a particularly useful example for us in studying astronomy is going to be, in fact, of motion without changing the speed. Let's look at it, and maybe it'll help clarify these concepts a little bit. The example we're going to want to study is the example of an object, say maybe a planet, moving in a circle about some center, say the sun, at a constant speed. So in this first pane, you see the black dot, which is our object, and it is set so that it is moving around a circle at a constant speed. Its speed is not changing. Its velocity, however, is clearly changing, because if I freeze the animation here, the velocity of the object, manifestly, is pointed in this direction. It's moving that way. Whereas, if I let the animation go a little farther and freeze it again here, the object is moving at the same speed, but in a different direction. And therefore, there is definitely a change in speed, and to quantify and understand that change in speed, we will move down to this pane, where I have put in the object's velocity. It is an object with a direction, so we draw it with an arrow, and the arrow at the beginning points up because that's the direction in which the object is moving, and as the object moves, the velocity changes because while the arrow is of the same length, its direction is continually changing. So this is the way your velocity changes when you move around a circle at constant speed. Coming down here, I've got two circles, the circle along which the object is moving, and then this imaginary circle. And if you look, what the imaginary circle does is I've copied the blue arrow over to here and drawn it so that its tail is always at the origin. So the edge of this arrow is giving me the direction, and of course the constant magnitude constant size of the velocity vector. When the arrow points to the right, the object is here and it's moving to the right, and so on. So this is my velocity vector v. Now I can understand how to measure acceleration. Acceleration is going to be the rate of change of this vector, so that if I freeze the animation at any given point, I can see what's going on. The object is over here, it is moving in this direction. That's why this velocity vector points this way. But I know where the velocity vector is going. It will next move over here to the right, so the vector that measures the change in velocity will point along this circle, just as the vector that measures the change in position points along this circle. To make that clear, here's the same two circles, and on this, here on the velocity circle, I've added a green arrow to represent the change in velocity. And as they play, you see that as the green arrow is constant in magnitude because the velocity is rotating at a constant rate, just because this thing is rotating at a constant rate. And the green arrow points along the velocity circle. And what this green arrow is, in fact, is our acceleration. It's the rate of change of the velocity. And so to make that explicit, I've here done 3 circles. This is the position circle, this is the velocity circle, and over here we have the acceleration circle, where I've taken the green arrow, the rate of change of velocity, and moved its tail to the center, so that at any time this gives me the rate at which the velocity is changing. So you can play with all 3 arrows, and I'll post this file so you can try to run it. The main thing I want you to notice here is that if you look, there's a relation between the directions of the acceleration arrow and of the position arrow. When the position arrow points here to the upper left, the acceleration is to the bottom right, and that's not a coincidence. Velocity is 90 degrees to position. Acceleration is 90 degrees to velocity, adding up to 180 degrees away from position. So when you're out here, your acceleration points that way, and if I move it and freeze it again, you'll see that this is always maintained. When you're at this position, your acceleration points in that position. So the acceleration at any given point is in fact, at any given time, is in fact pointing directly to the center of the circle. If you ask, in which direction is this object moving? It's moving along the circle. In what direction is it accelerating? That way, towards the center. So we found that moving in circular motion at a uniform speed, you're experiencing an acceleration of constant magnitude, always directed towards the center of the circle. Now, if it's important for us to understand this circular example better, so let's go through it. If the radius is r and the speed v, I want to know, we know the direction of your acceleration. What is its magnitude in meters per second squared? So I'm looking for an acceleration in meters per second squared, and it needs to be determined by, what is there to determine? The fact that you're moving around a circle of a given radius at a given speed, and we all have an intuition that if you're going faster around a curve, you'll need to accelerate more to take the curve. And if the curve is a tight curve, you need more of an acceleration. So let's see if this is borne out, and we'll use a trick that physicists use. It comes from units. We're going to do what we call dimensional analysis. We need to find some combination of r and of v that could, in principle, be an acceleration. And it turns out there's only one. Because if you think about it, r is measured in meters. It's a length. V, being a velocity or a speed, is measured in meters per second. We need to fashion out of these something that could potentially equal a. And it's clear that the only way we're going to get seconds squared in here is to take the square of the velocity. So write the square of the velocity. This is a good idea, but that has units of meters squared per second squared, because it's the product of 2 things with units meters per second. So that's not quite right. This does not have the right dimensions, but we need to clean out the meters, and to clean out the meters, we can simply divide by r, which is measured in meters. Now, dimensional analysis doesn't always give the exactly right answer. If the acceleration could easily have turned out to be 3 pi times v squared over r, and the 3 pi would not show up in dimensional analysis. In the case at hand, it turns out that there is no constant. You can do the calculation. It takes a little bit of effort, but we're not going to do it. The answer is that we got the right answer. For precise, correct expression, using just this dimensional analysis. So the acceleration towards the center of a circle is given by v squared over r. It has the fancy name centripetal acceleration because it is towards the center. And this will show up often in what comes next. We now have a nice way to state Galileo's principle of inertia. An object upon which no external influence acts moves with constant velocity, or equivalently, has zero acceleration. Now we step it up. What happens when an external influence acts? And Newton introduces a brilliant concept here, which is the external influence is quantified by something called a force. What is a force? It's a tricky concept. A force is that which causes acceleration. The idea that Newton introduces is that you can imagine applying the same force to two different objects. And we all have that intuitive idea. I can give an identical push to a tennis ball and to a refrigerator. And we all have the intuitive idea that we'll get more of a motion out of the tennis ball than we will of the refrigerator, because the refrigerator is heavier, or technically the refrigerator has a larger mass. And so Newton quantifies this intuition in the idea that there is such a thing as a force, something that measures the amount of external influence being applied to an object, and the object's acceleration is related to this force by a property of the object itself known as its mass. And the mass is roughly the amount of stuff in the object, all counted, weighted appropriately. It's measured in kilograms, and an object that is massive is an object that is heavier. We'll make that precise in a second. And force, like acceleration, has a direction. You can push something to the left or push it to the right. And so we have this new physical concept of force. We need to understand what units we measure force in, and that follows directly from this equation. A force of 1 unit is a force that causes a mass of 1 kilo to accelerate at 1 meter per second squared. So the unit of force is this unit, kilogram times meter per second squared, and it is dignified, of course, with the name Newton and denoted by an N, so that would be a force of 1N. Before we go on to clarify some details here, let's go on to Newton's third law. This was Newton's second law. And Newton's third law explains why there has to be an external agent applying the force. And this is crucial. Newton tells us that universally, when an object A is applying a force to B, and the force is given by F, which means B is being accelerated, something is applying the force, go find the thing that is applying the force, then B automatically reacts on A, we call it, and that means B applies to A force that is equal in magnitude and opposite in direction. We write it mathematically as negative F. Negative, a vector, means a vector of the same size pointing in the opposite direction. What this means is that when you push on the refrigerator pushes back on you. This is not an action by the refrigerator. This is not some act of will. It's Newton's third law in action. Now, let's do an example of this. It was known already to Galileo that if we let loose some object, we all know this, if I let something go, this ball right here, then an external force will act on it. How do I know? Because the ball has an initial velocity of 0, and clearly it does not maintain the initial velocity of 0. It begins to move downward, so it has a downward pointing acceleration. And in fact, this acceleration was measured by Galileo and people after him, and it has the interesting property that it is uniform